So let's look at what impact the rocket equation has on the actual construction of rockets and rocket engines. First of all, we saw that the rocket equation puts a limit on how much of the fraction of the mass of the rocket can be devoted to the actual structure and the payload. In other words, you want to make rockets as light as possible. And this is an extreme example, the Mercury Atlas II, which took John Glenn into orbit. The Atlas II rocket, in order to reduce its body weight, had an aluminum skin that was so thin that it had to be constantly pressurized in order to maintain its structural integrity. If it lost pressure, the whole rocket would just have collapsed. So that's a real extreme example. Most rockets can support their own weight, but this rocket was so light that it couldn't even support its own weight. And then, of course, we saw the tremendous difference that the exhaust velocity makes, which means you want to have as high an exhaust velocity as possible, which means you want the temperatures and pressures in your combustion chamber to be as high as possible, which means you are really pushing all of our knowledge of metallurgy to get materials which aren't going to just melt. And we don't have metals which will tolerate long exposures to rocket exhaust. So we need some way of preventing the rocket nozzle from just melting. And so what typically is done with a modern rocket engine is, particularly for when you have a cryogenic fuel like liquid hydrogen, which is really, really cold, before it goes into the combustion chamber, you actually run it through a whole series of pipes which go up and down the outside of the nozzle. And this serves two purposes. First of all, it absorbs a lot of the heat, so it keeps the nozzle cool enough so that it doesn't melt. And of course, it preheats the hydrogen, which gives it that much more energy when it gets into the combustion chamber. So you want to keep the structure of the rockets as low as possible, minimize the structural mass, and you want to increase the exhaust velocity of the propellant. Those are the two critical things that we have gotten out of the rocket equation. A dream of rocket scientists for generations has been to build a rocket which can take off from a launch pad and fly to orbit. But we just saw that even for cryogenic hydrogen and oxygen, you still would need a structural fraction of only about 10%. And that's really hard to do because of the rocket equation, and that limits the amount of structure that you can put into your rocket. And that's basically why rockets which go into orbit, at least with our current technology, all have stages. There's the famous Saturn V rocket, and you can see that actually had 3 stages. It took the first two stages to get into orbit, and then the third stage actually pushed the astronauts on their way to the moon. So we're going to actually have you all work out a problem in rocket staging. I've found over the years that that's the best way to give you a feeling for why you gain so much by staging a rocket. But in order to help you to do the problem, let me just run through how we would set up the problem. It's basically very similar to the way we looked at a single stage rocket before. We still have just one payload up at the top, which we're trying to get to orbit, but we have 2 separate rocket stages. We have the first stage and the second stage. That's stage 1 and stage 2. Now, when we're firing the motors of the first stage, and it's sitting on the launch pad, we have to get a little bit more complicated in our equation because we're going to keep track of the 2 stages separately. So the initial mass at stage 1 ignition initially is the structure of the first stage, the propellant that's in the first stage, the structure that's in the second stage, the propellant that's in the second stage, and of course the payload. What happens after the first stage burns out? Well, we have everything we started with except no more propellant in the first stage. We still have the propellant in the second stage because we had to carry that along with us. Now, what we do when we stage a rocket is we drop the first stage so we get rid of the structural mass. And this, of course, is the whole point of staging. We're now lighter when the second stage fires. And when we finish, we have burned the propellant in the second stage, and we're just left with the structure in the second stage and the payload. Now, let's look at the rocket equation. In the first stage, we are using the initial divided by the final mass of the first stage, and we already saw what those were. And then we'll get a second velocity increment using the propellant that we have in the second stage, and we'll find out what that is when we take the ratio of the initial to final stages, masses in the second stage. Just for simplicity, let's assume that the exhaust velocity of the first and second stage engines is the same. Obviously, that doesn't have to be the case, and it's often not, but it makes the math a lot simpler. So I'm not going to run through this in great detail, but remember that the logarithm, the sum of two logarithms is equal to the product of the two arguments, and we notice that we have, therefore, the total velocity that we get is equal to the exhaust velocity times the natural log, and you can see it's the initial masses of the first and second stages and the initial divided by the final masses of the first and second stages. And just to show that we're on the right track, if we didn't have any staging, then we wouldn't have dropped the mass of the structure of the first, and in fact, therefore, the initial mass of the second stage would be equal to the mass when the first stage cut off. Of course, we couldn't light the engine, but we're just doing this theoretically. And so we would get back to the total delta V in relation to the initial and final mass, just as we had for a single stage rocket, which is what we would expect, because if we don't drop the first stage, then essentially we have a single stage rocket and we're just burning it in two stages. That's assuming that we could burn the second stage engine without dropping the first stage. So we're on the right track. This is the way I want you to set up the problem. We'll post the problem, give you the numbers to put in, and by looking at how much of a payload you can actually carry for a given amount of propellant, either all burning in one stage or separated into two stages, as I've shown you here, I think it'll give you a real understanding of why we stage our rockets. So that'll give you some work to do. And when we come back, we'll talk a little bit about what happens when you actually have to start flying through the atmosphere and launch off the surface of a planet.